In this video, we are going to see about stress, strain and elastic constants. So if you want to know about the stress, strain and elastic constants, it is essential to know about what are the forces and types of forces and what are the difference between force and load and elasticity and plasticity and different types of elastic constants like Young's modulus, rigidity modulus and bulk modulus, and finally the Hooke's law, Young's modulus. So in the blacksmithy workshop, right, so the metal is heated and it is beaten to get the required shape and size. Similarly, when the metal is subjected to a stretching force, like we can see the length is increasing, at the same time the diameter is decreasing. So the axial force, which is a push force or a pull force, if it is a pull force, it comes under tensile force. If it is a push force, it comes under the compressive force. Force is an external agent capable of changing the body state or rest. Force is a push or pull of an object resulting between the two objects. So force has magnitude and the direction. From the basic principles, we can tell force is equal to mass into acceleration. So either if you have a body, you can move the body, what happens? You can push the body to move or you can pull the body to move. So force is an external agent which is pull or push to change the body's state condition. So coming to the load, load is defined as the combined effect of external forces acting on the body. The different types of loads are tensile load, compressive load, shear load, torsion load, flexural load and buckling load. So in the tensile load, you can see a stretching force is applied along the axis of the object. Similarly, the compressive load, the pushing force is applied. The difference between the tensile and compressive load is, so in the tensile load, what happens? The body elongates. In the compressive load, the body contracts, the size is contracts, the length is contracting. At the same time, the cross-sectional area is increasing. Coming to the shear load, shear, the forces, it is acting on the shear plane. So the torsion load is nothing but the twisting force. Similarly, the flexural load is nothing but a load acting on an object to bend. So coming to the tensile force, consider a body, a cylindrical object of diameter d and length L. It is subjected to a axial pull force. It is at initial condition. So after the object force is applied, the length is increasing, that is L is changed to del L and the diameter is decreasing to d minus del d. So the tensile force is a force, it is acting away from the body across the same line of action. So you can stretch the object, while stretching the object the diameter is reducing and the length is increasing. Coming to the compressive force, it is opposite to the tensile force. So the same force intensity P is applied towards the object. So what happens here, the length changes, L changes from L minus del L. Similarly, the diameter changes from d to d plus del d. So while compressing, what happens, the length is reduced and the diameter is increased. So this compression is usually applied in the case of bricks and concrete. So this is to show the difference between the tensile force and the compressive force. So you can see the point pull, the initial diameter d and with the length L is changed to d minus del d. So the diameter is getting reduced in the tensile force and the length is getting increased in the tensile force. So the compressive force is in the push form. So the L is changed to L minus del L. So the length is reduced here and the diameter is changing to d plus del d. So that is diameter is increased in the case of compressive force. So coming to the stress and strain, when the object is subjected to the force, right, so there will be the internal resistance offered by the body against the deformation. So that internal resistance is called stress. So the length is L, it's taken in mm. So the d is the diameter of the bar taken in mm. P is the tensile force or the tensile load acting on the body. So change in length here is positive in the linear direction. So L is changed to L plus del L. So it is called as positive deformation, and then in the lateral dimension diameter is getting reduced, so it is a negative form. So diameter is D is changed to D minus del D. So coming to the stress and strain in the compression form, so here the push force is applied. So coming to the chair, the change in length is negative. So length gets reduced, at the same time the diameter gets increased. So in the linear direction you have the negative strain, and in the lateral direction you have the positive strain. So coming to the stress, stress is the internal resistance offered by the body against the applied force. So the stress is the ratio of load per unit area. The unit is Pascal, that is Newton standing on meter square, or kg per meter square, kg per meter second square, or joules per meter cube. So coming to the stress in the different sections, so the section may vary. The beams have either solid circular section or solid rectangular section or solid square section or hollow rectangular section or hollow circular section. So based on the circular sectional area, the area we want to substitute as, either you have the circular, you want to substitute as pi by 4 d square, rectangular can take it as L into B, square section you can take as A square, hollow rectangular section, so outer section area minus inner section area, and hollow circular section similarly outer circular section minus inner circular section area. So coming to the strain, strain is the deformation of the material from the stress. So it is simply the ratio of change in length to the original length. So in general we can tell us strain is the change in dimension by original dimension. In the linear direction you can take, that is across the length direction, linear strain will be acting epsilon 1, that is change in length by original length. In the lateral direction, that is in the diameter section, change in diameter by original diameter. So coming to the Poisson's ratio, it is the, when the body is stressed or compressed, right, within its elastic limit, what happens? The length is reduced, at the same time the diameter gets increased. So at which ratio it increases or decreases? The Poisson's ratio is the ratio of lateral strain to the longitudinal strain. Here we denote the Poisson's ratio by the mu, or 1 by m, that is nothing but lateral strain by linear strain. That is lateral strain in the sense strain acting in the diameter side, and linear strain is the strain acting in the length side. So Poisson's ratio is 1 by m. So for the circular section you have only one lateral section. For the rectangular section you have breadth and thickness. So you want to take this in mind. And coming to the Poisson's ratio application, for example, you can take the example for rubber, the rubber block. If you apply the compressive force, right, what happens? It changes its length or changes the dimension in both the sections, sides. So it should not, it should change the side in equals. That's why we are getting lateral strain by linear strain. So if the lateral strain is 1 and linear strain is 2, 1 by 2 will be getting as 0.5. So if the rubber, consider the rubber is used in the bottle, right, to close the bottle cork, instead of a cork you are using the rubber. If you are applying the compressive force, what happens? If you are applying the force and the direction of P, and what happens? The rubber will stretches its direction in the diameter type and it gets locked into the bottle. So we need a material which has certain property, that is, it should have the property when I compress, it should not change the direction in the lateral direction. So we need a material, want to select a material, that's, it is cork. So when the cork, that's why the cork is selected as a material for closing the bottles, right. So even though if you apply the compressive load, it will not change its direction. So the Poisson's ratio is 0 here. So coming to the shear force, the shear force lies in the plane of the area. It is developed when the external loads tend to cause the two segments of the body to slide over one another. The best example is the two plates are connected by means of a rivet, right, and a pull force is applied. So what happens? the rivets get sheared. So here forms the applications of a shear strain. The best example is the cutting of fruits, vegetables, or shearing of paper, painting or brushing or applying the creams over the surfaces, right, and chewing the food between the teeth forms a good example of the shear force. So another best example is just a punching machine what we are used to put a holes on the paper, right. So what happens, the punch gets sheared, apply the shear force so that the punch hole is formed. So this is the example of blanking and punching operations, right, the same principle, but the workpiece and the scrap is different, right. So the guillotine machine, which is used to shear the head for the olden days, right, for giving the punishment and all, right. So coming to the bending, bending is the act of changing the component from straight form into a curved form or an angular form. Just imagine a surface having a rod having the straight surface, right. So what happens when you apply the load, it bends. So when you apply the force at the center, the object bends. So at what strength at maximum it can withstand? It is checked with the help of universal testing machine, and the respective strength is called as bending strength or flexural strength. So coming to the next thing, elasticity, right. So the elasticity is the ability of material to deform under the load and regain its original shape when the load is removed. Take the example of a rubber band. When you stretch it, what happens? It elongates. When you leave it, right, it regains its original position. So the form of regaining the original shape when the load is removed is called elasticity. So coming to the plasticity, what happens? The same thing, if you apply the load, the body changes its form, right, and when you release the load, it doesn't comes to the original position. Some form of strain is present here so that the body do not regain its original shape. So this ability of material to deform under the load and do not regain its original shape when the load is removed is called plasticity. The best example is making the clay pots, right, where they are applying the pressure to get the required form of the parts. So coming to the elastic constants, so there are three elastic constants. Based on this constant value, we can tell which type of material it is. One is Young's modulus or rigidity modulus, Young's modulus or modulus of elasticity by E, and rigidity or shear modulus represented by G, and bulk modulus represented by K, and Poisson's ratio represented by mu. So mu is equal to 1 by m. So in the solid material, Young's modulus is commonly used. In the fluids, where the objects or the liquids or gases, right, anything it is capable of flowing, we can tell it as fluids. So the concept of bulk modulus is used in fluids. So coming to the Hooke's law, it is stated by Robert Hooke. So what happens when the body or when the material is stretched within the elastic limit, the stress is directly proportional to the strain. So the Young's modulus is framed here, E is equal to stress by strain, that is within the elastic limit. In the graph you can see when the object you are applying the force, right, what happens? The stress is proportional to strain at one point up to this one particular level, that is elastic limit. Even though if you release it, what happens? The body attains its original shape. After that elastic limit, what happens? Even though if you have the applying the force, what happens? The material deforms, then finally it gets into fracture. So coming to the Young's modulus, it is the measure of the object's rigidity, right. So when the Young's modulus is very high, the object is very rigid, and the Young's modulus is very low, it is very flexible. Just in the case of a rubber hose where you can bend easily. Similarly, a steel rod which can be very tough to bend. So the Young's modulus is the measure of object's rigidity. So in the graph you can see the foams have very light very flexible, then comes the wooden products, green color, then comes the composites, then finally the ceramics and metals are very stiff. So that's why we cannot able to bend it. So the stiffness and rigidity, the both are common terms. So coming to the rigidity or shear modulus represented by G, it is the measure of the rigidity of the material. So rigidity modulus can take shear strain by shear stress by shear strain represented by G. So coming to the values, you can see the wood has 6.2 into 10 power 8 Pascal, and concrete has 2.1 10 to 10 power 10 Pascal, and steel has 7.2 into 10 power 10 Pascal. So looking into it, steel has higher value of rigidity modulus, so that we can tell steel is a very rigid compared to wood. So the relation between the Young's modulus and modulus of rigidity is given as E is equal to 2G into 1 plus mu. So G is rigidity modulus here, E is Young's modulus, and mu is the Poisson's ratio. So coming to the bulk modulus is the measure of the resistance of the material to compression. So when you compress the body or compress the material, how it behaves. So based on the bulk modulus value, we can tell the performance or the behavior of the material under compression. So the bulk modulus is represented by K. The force is applied per unit area divided by volumetric strain due to compression. So the relation between Young's modulus E and bulk modulus K is given by E is equal to 3K into 1 minus 2 mu. So these are the equations to remember, right? Stress is represented by sigma, which is equal to load by area, P by A. So load unit is in Newton, area in meter square or mm square, will be getting as Newton per meter square or Newton per mm square. So units are very important. Strain is represented by the ratio of change in dimension to original dimension. So since this is a ratio, there is no unit, right? Similarly, the linear strain is change in length by original length, the del L by L. Similarly, lateral strain, the strain in the diameter direction, that is change in diameter by original diameter, that is del D by D. Similarly, the Poisson's ratio is 1 by M, lateral strain by linear strain. So the lateral strain is the strain acting on the either the diameter side or breadth or thickness side, divided by linear strain, that is strain acting in the linear direction. It is also having the no unit. Coming to the Young's modulus, E is equal to stress by strain. E is having the relation with G. E is equal to 2G into 1 plus mu, and E is equal to 3K into 1 minus 2 mu. So in this lecture, you have seen what is the force and what are the types of forces, what is the difference between force and load, the stress sigma, strain epsilon, and the Poisson's ratio. We have seen what is the difference between stress and strain and Poisson's ratio, and what is the difference between elasticity and plasticity with the examples we have seen, and the elastic constants, Young's modulus, rigidity modulus, and bulk modulus, and its relations with Poisson's ratio we have seen, and finally the Hooke's law and the formation of the Young's modulus.